So now we go to Discrete Life Annuities, the last section for annuities. So annuities where payments are made if and only if X is alive at the time the payment is due. There are two types of life annuities. First is annuity immediate and second one is annuity due. So annuity immediates paid at the end of each year. So for example, we draw the timeline. So annuity immediate is paid starting from first year, second year, third year at the end of the year. However, for annuity due, payment at the beginning of each year. So for example, if we draw the timeline, so the payment will start from 0 because it starts from the beginning of each year until it will stop until omega minus 1. So now we go to whole life annuity due. Same as annuity for the continuous case. So annuity due also have the case for whole life. So annuity due starting at 0 because it at the beginning of each year. This is for the case for annuity immediate starts from 1. So the relationship between annuity due and annuity immediate is 1 plus annuity immediate. So this is annuity due for whole life. This is annuity immediate for whole life. So the APV for annuity is the summation of VK times KPX. So since it is annuity due, K is start from 0 because the payment is start from 0. And it is until infinity since it is whole life. And we only considering KPX because it pays for survivors only. And this is a recursive formula for annuity due. So we draw the timeline. We start from 0, the payment. So at omega, it equals to 0 because we pay until omega minus 1. And then, since it is recursive formula, so we discount all to t equal to 0. So that's why annuity due is equal to 1 plus V, the discounted factor, times PX times annuity at X plus 1. So this one plus all the payment. As a recall, annuity also can be derived from the insurance. So as the continuous case, AX is equal to 1 minus insurance over delta. So delta is force of interest. So for discrete case, instead of delta, we use discount. So D for discount. Then we get this formula from here. However, for your syllabus, we do not find the life insurance for discrete. So this is life insurance for discrete because we do not cover for the life insurance for discrete. We only use commutation function. So commutation function is this one. So we have to refer the table to find the value for nx and dx. Later on, I will show you the table. So whole life annuity immediate. So the notation is AX denotes the actual present value of annuity 1. So the payment we assume is 1 for each interval. So the relationship between annuity immediate and annuity due is this equation. So the summation of VK KPX. So the difference only the K, we start from K equal to 1 since the payment start from 1 until infinity since it is whole life annuity. So for commutation function, the difference between annuity due and annuity immediate, so nx plus 1 over dx. So this one we have to refer the table. So the difference only the numerator. So the numerator is at x plus 1. Denominator is still same, dx. And then the third one is annual temporary life annuity due. So it is paid for a specific term. Let's say we assume at 1 ringgit for each interval for the next n years, provide a life now each x is then alive. So from 0 to n, the APV is this one, and this is for the case where still survive more than n years, it will get until n years. So the present value is VKKPX. This is for due. So this is how we write down the notation, because we have term n years. So the upper bound is n minus 1, and we start from 0 since it is annuity due. So the payment will be until n minus 1. So that's why the upper bound is n minus 1. So this is the relationship between annuity due and annuity immediate. And this is the commutation function. So nx minus nx plus n over dx. So far, for whole life annuity due, the commutation function is equal to nx over dx. And for temporary life annuity for n years, nx minus nx plus n over dx. And for n-year temporary life annuity immediate, so same case as annuity due, but the difference only it paid at the end of each of the next n years. And the APV is starting from 1 to n. So the payment 1 ringgit until n years, as long as the annuitant still survive. And this is the notation for the APV for n-year temporary life annuity immediate. And the commutation function is equal to this one, nx plus 1 minus nx plus n plus 1 over dx. So for annuity immediate, we have two types. For whole life annuity immediate, AX nx plus 1 over dx. And for n-year temporary life annuity immediate is equal to nx plus 1 minus nx plus n plus 1 over tx. So the difference between annuity immediate and annuity due only the numerator for both case. Last one, deferred annuities. So deferred annuities where the payment does not begin immediately but it is deferred for 1 or more years. So this is the notation for the APV. And year deferred, how many years for the deferring. So the relationship between annuity due and annuity immediate. So the payment start from here for annuity due. So for annuity immediate, let's say 10 years, n is equal to 10. So it starts from 1 until 10 years, for example. So this one is equal to this one, the annuity due for whole life until omega minus 1 minus this payment because it deferred for n years. So we also can use this equation. And the present value random variable, if the death happens, so the K is time of death for discrete case. Is the death happen before n years, so the benefit would be equal to 0. And if the death happen at the n years or after n years, so this is the benefit that will be paid. So the commutation function, this is how we write down the deferred life annuity due, and the numerator is nx plus n, but the denominator is still the same. So for annuity immediate, still same as annuity due, but the K is start from n plus 1. So for due, we start from n. So if the death happened before n years, so no payment will be made. If the death happened at n years or after n years, so this is the present value random variable. So this is the notation for annuity immediate. So the difference only the numerator, nx plus n plus 1 over tx. So the last one, this is for life annuity with monthly payments. So meaning that the payment paid more than once for a year. It can be monthly. So if monthly, 12 payment will be paid for 1 year. If let's say quarterly, so every 3 months. So it becomes 4 times a year. And for semi-annual basis, meaning that every 6 months, it becomes twice a year. So this is the notation for annuity due for monthly payments. So M can be 2 for semi-annually, quarterly can be 4, and 12 for monthly. So first payment is made at age X because it is due. So now we can try the exercise. So A, find the actual present value of a whole life annuity immediate issued to an annuitant age 45 using the ILT at 0.06. So ILT is the illustrative life table. So 0.06 is the interest. So the interest at 0.06. So this is the table, the illustrative life table. So we have the age, the first column, and the second column is DX, is the number of survivors, and X, and we have SX. But for this course, we just cover for the first two columns, okay, DX and X. Alright, we try number 1. So number 1 is whole life annuity immediate equal to N46 over D45, because annuity immediate is NX plus 1 over DX. Then we refer to the table N46 and D45. So here, so N46 and D45. So then we plug in into the equation and we get this one. And let's try number 2. Find the actual present value of whole life annuity due issued to an annuitant age 45. So for this case, it is equal to NX over DX. Okay, for annuity due. So the numerator and the denominator, the age is equal. Then we refer the table N46 and D46, the values inside the equation. And you can also try C and D. So for C and D, for the case of temporary, so we have N years here, and the numerator, we have to use NX plus 1. This is NX plus N plus 1. For the denominator, still the same. And for D is for the deferred case. So this is NX plus N plus 1, and this is NX plus N. So you can refer to the table to get the values for B, C, and D. The actual expected present value of annuity pays 1,000 at the beginning of each quarter, while X survive is 4,000 AX4. So meaning that this is for the case of payment paid quarterly for each year. So M is equal to 4. So that's why we put 4 here. And the payment is 4 times 4 each year, and it starts from 0 since it is due. And this is for the actual present value, or the expected value of Y. So from here we get this one. So this is the relationship between annuity and insurance. So since it is discrete, so the insurance also discrete. And this is how we find the variance from the expected values. And to find this, we have two types of assumption. So we have UDD assumption for uniform, and the second one is traditional approximation. So to find the APV for M times, so this is the basic formula. So the difference between UDD and the traditional assumption only how to find the alpha M and the beta M. So the alpha M for UDD is this one and beta M is this one. So we use D here. D is for the discount. So how to find the discount? So discount is I over 1 plus I. So how we get this one? This is the relationship that we cover in chapter 3, where I show you E delta, how to convert in terms of I, how to convert in terms of discount, and the discount for M, and the interest for M payment. So you can refer back to in chapter 3. So the relationship is 1 over 1 minus D equal to 1 plus I. So this is the power of negative 1. So this relationship we use to find this one, to find D. So finally we get D is equal to I over 1 plus I. So example 3, on the basis of ILT, so ILT is the illustrative life table at I is equal to 6%, compute annuity for quarterly at age 25, annuity due using both assumption, UDD and traditional. So M is equal to 4 and X is equal to 25. So this is the basic equation to find this annuity for monthly payment. So we have two types, UDD and the traditional. So the difference only the alpha and the beta for both case. So for traditional, it's just simpler because the alpha is equal to 1 and the beta only M minus 1 over 2M. The complicated is for the UDD case. So let's try the UDD first. So we have to find the alpha, ID times I4 times D4. So we find the alpha for UDD. So using the formula given, D is equal to I over 1 plus I. So now we want to find I4 or IM or and D4. So we use this relationship, okay? So I4 is equal to this one. And then from here we also can find D4. So D4, so we just substitute I with I4. And then we get D4 is equal to this one. Okay, so we get value for D4 and I4, then we can substitute in alpha. So the alpha is equal to 1.044, and also we can substitute in beta 0.3998. Then we have to find A25. So A25 is N25 over D25, and we refer to the table at age 25, and we substitute the values, and then we can solve this equation. So this is for alpha times the annuity at age 25 once payment per year minus beta. Okay, so you also can try for the traditional approach. And example 4. A pensioner aged 55 is undecided whether to receive his 250,000 as a lump sum or on monthly basis. So monthly basis M is equal to 12 as long as he is alive. If he chooses the later, so the later refer to example 3, which is UDD and traditional. So the later method, meaning that for the traditional, what will be the monthly amount due to him? So we use traditional approach, and we have to find this annuity. M is equal to 12, X is equal to 55, and this is the amount. And then this is the basic formula for both cases, traditional or UDD, but the difference only how we determine the alpha and the beta. First, we find the annuity at 55 for once payment per year, and we have to refer to the table N55 and D55 here, this row, and then we substitute the values and we got 12.2758. Then we find the alpha. So alpha is 1 for traditional approach, and so for beta it is equal to m minus 1 over 2m. Deferred case for monthly payment. So this is the equation. Okay, that's all for chapter 4.